Welcome to Qt Widgets and More. In today's episode, we're going to attack a problem from the ancient time, namely how do you return values, multiple values, mind you, from a function. More specifically, we'll see how structural bindings works together with the special Qt type QHash and QMap, and more so, we'll see how they become beautiful whenever you iterate over the elements of a QMap or a QHash. Stay tuned. Let's jump right into the code and look at what did it look like in the really old days. I have this function here, split path. It takes a path, as you can see down here, and it splits out the base, and the extension, the base is my file, and the extension is MP5. Okay, it's from the future. So in this split here, what I need to do is return two things, namely the base and the extension. So I take them in as references to QString. As you can see down here, I create my base and extension, I call my path, and they will be magically filled. Of course, there was lots of discussion back then whether it should be pointers or references. And at some point somebody said, well, why don't we return a record? Or struct. So we returned struct, and it was annoying that we needed to create structs just to return those. And at some point somebody came around and said, hey, let's create a kind of meta struct, namely a tuple, or for the specialization of two, a pair. And that's what it looks like. In the next step here, I return a pair of strings and strings, and now QMake pair here return that, or create that pair, and I can return this. And this code works perfectly fine with C++11. In C++14, 17, you don't even need the QMake pair anymore, but back then you did. We also have a version here that returns a stud pair, and in C++11, we already had the beauty of a new construct here called stud tie. So my split path returned a stud pair, and over here I could unpack it right where I called the function stud tie, base, and extension. There was just one problem with stud tie, namely that I needed to declare the base and extension names before I called stud tie. And what I really wanted was just something that smelled like Python, where I could just write the names right on that line and invent them on the line where the return was. But unfortunately, C++11 didn't allow that to me. But 2011 is 11 years back now. And in 17, we got this new thing called structural bindings. And let's see what it looks like with structural bindings. So with structural bindings, the code down here now looks like this. It's still returning a stud pair as before. And down here I write const auto reference square bracket base comma extension. And had I been an actor, I would have been shedding a tear now in joy. Fortunately, I'm not an actor, as you can tell, and I'm not too thrilled that I need to write const auto reference. But hey, that's the boundaries that we are within in C++. So I'll just accept that I write that. At least I don't need to have two lines declaring base and extension anymore. It also works with QTuple or QPair, as we had from the Qt world. Exactly same code. And actually, it even works with my own struct. So if I have a struct up here, I can just unpack it with structural bindings. And that, of course, led me to, well, how far can I take this? And at the end of this video, I will show you step number 7, structural bindings with my own class, but you'll stay tuned for that, because first, we need to discuss when are they even interesting, because otherwise I'm gonna lose you here and you'll click onto the next kitten video on YouTube. So why are these structural bindings interesting? They are not interesting to avoid writing string, base, string, extension, but go straight onto getting the base and extension. No, they are interesting when you iterate over a QMap or a QHash or the C++ counterpart from STL, the ordered or unordered map. And in those situations, it's interesting because you will get the value and key out of the map right away. But let's jump right over to me in the small version and see the code. So what we see here now is a const auto reference key comma value on my map. And my map is a stud map up here with a bunch of items. And I can just iterate over it like this. And there's no more dot first and dot second. I can even modify the elements in here. So instead of a const auto reference, just auto reference key comma value. And now I can modify them. And just to show that it worked, I printed out. So let's see, ranges STL maps in loop. It is right up here. Ranges STL map in loop. They are modified 1, 1, 2. Well, that's the unmodified version where I print out the key and the value here. And here I now have modified them, which you saw by adding these arrows on each side of the value. No, stop. Don't go over to those Qt videos yet if you're a Qt developer, because it doesn't work that well out of the box with our good friends QMap and QHash. And let's see why that is. Remember, a few months back, I had an interview with Pepe on Q as const, and he explained to me that a range-based for loop basically is just a regular old-style iterators behind the scene. And if you look here at Take Two, you can already see what these look like back then. We asked for the begin or the const begin of our map. That gave us an iterator. We compared that against the end and plus to go next. And the key thing was that we looked at the values with asterisk IT. Okay. Go up and look at the range-based for loop here. There is no iterators, no nothing. But when I print out the value that I get assigned here is, of course, the asterisk IT. You can see that's 4, 5, and 6. So the Qt version of the map, it just gives me the values of the items that I'm iterating over. But what the structural bindings expects is that you'll get a pair that it can unpack. And I don't get a pair here. So unfortunately, that doesn't work with my structural bindings. What I need is a pair when I iterate. And fortunately, there is a version called const key value begin that was added for exactly that purpose, or likely added before, namely because we have the same problem with algorithms in C++. So therefore, we have these const key value begin, const key value end. And what that does now is it returns a stud pair of the key and the value. And I can access those with pointer first, pointer second. Yes, I know you're getting impatient and want to know how you can iterate using range-based for loops over a map or a hash from Qt, and that's exactly what we're going to see now. We had the problem that the iterator did not return the right thingy, namely a stud pair. We found that there was an iterator that did that, and that's the iterator that we need. But that's not the iterator that .begin is going to provide us. And we didn't see the .begin in the range-based for loop, did we? No, we did not. C++ calls that automatically. So we need to wrap this in something that gives us that other iterator when we call .begin. And that's what the small instance of me is going to tell you exactly how to get. Yes, that is me. That is a small version of Jesper that knows it all. I create this class called sRange. It's a wrapper around a container, as you can see here, and it implements just these two methods that the structural bindings will be calling to get the iterator, namely begin and end, and they do not provide the regular begin and end iterators, but instead these const key value begin and const key value end. And if we scroll down, there's also a mutable version here that calls the key value begin instead of the const key value begin. And now you can see here, I have my QMap. I want to iterate using the structural bindings. And for that, I simply call sRange around my map. I can also modify so smutual range around my map. And now I can modify the values in here. The ampersand is because that the smutual range is returning a proxy that is going to be a temporary. So we need, let's not go with that. the S range again here to print it out. And as you can see, it also works with hashes. So if you are in a hurry, it's okay, you can leave now. Thank you for watching yet another episode of Qt Widgets and More. But if you're not in a hurry, stay tuned for 2 small nitpicks on this code base here. First of all, I want to show you why I took a container reference in the S range rather than a const container reference in the case where it was not mutable. That's very subtle, but very deep stuff that you really want to understand if you ever use this code. The second thing is I would like to show you how I can create bindings for my own classes, structural bindings, so that I can write those. And I have examples for both of those. Let's start with the const in the S range. The const I'm referring to is here. Why didn't we take a const container reference? And yeah, I need to make this one down const here too. That's cool. But why didn't I do that? That's what you usually do when you have something and it's the container is gonna be accessed via const key value. So let's see. It does compile. Why? I must have been drunk. Nothing to see, carry on. Well, we do carry on it. One day I'll be doing like this. I'm just creating a method container. Let's call it container, shall we? Get container that returns me an instance here. What is the value that I get there? Well, it's a temporary, right? So if I go down here and I now, instead of this one here, I call get container. That should be fine. I wrap my container and we run it and it compiles. But see the output here. Lots of weird stuff. If any of my viewers out there is from a country that understands this, I would like to know what that symbol means. It likely means, Jesper, you are a bloody idiot, because you, of course, should know that there is an issue with lifetime here. Get container returns me a temporary. The temporary will go out of scope as soon as we hit this closing brace here. So it goes out of scope, it gets garbage collected. As range, on the other hand, is remembering a reference to that one. So that's a temporary that I remember a reference to, and temporary gone out of scope. That is why I see all of these things. And that is why I said, let's not have const here. If I do not have const here and I try and compile it, it will tell me, sorry, you cannot bind an R value to this because I cannot find any methods or any instantiation of your S range class here where I can give it an R value. This one is an L value. Yes, I should very likely have added a comment above saying this must be an L value, otherwise you have the problem with temporaries and whatnot. That's another solution to this, namely to implement the R value version of my constructor. And let's see what that looks like. The R value version means that I'll make this const again. And let's just, maybe I should have copied before I made it const. Of course, now I need to remove the const again. And what I'll be doing here is ampersand, ampersand. It still needs to instantiate this. And down here, qfatal, you can only give L values because how would I have a reference to the R value? Potato, potato, but there's another solution for you. You want to really see that it works? Well, I can compile it and I can even run it and it gives me an error because I forgot the semicolon here. Why is there all these semicolon requirements in C++? Now, of course, I need to make this one const down here again. Why did you want me to show it that it worked? Your fault. And there it is. And you ... That's the qfatal that hit there. But I actually like the other one because that gave me the error already at compile time. And finally, I would like to show you how you can implement your own unpacking mechanism for structural binding, namely for classes where you do not just have a tuple or a pair or the Qt version or a regular struct just with public instance variables. And why do you need that? Well, honestly, I don't think you ever need that. But when I did this just to practice with it, there was quite a few flashbacks to the episodes on implementing some template code that I found very useful, and that's why it's in this episode nevertheless. If you're leaving already now, see you next time, but otherwise, stay tuned. We are back to the split path here. The split path this time returns a MyStruct, and the MyStruct is this class here that has the base and the extension just as before, but it also has a method for calculating the full length of that file name. And that part isn't a instance variable, and besides the string for the base and the extension isn't instance variables either. So the regular unpacking of structs doesn't work here. We need to answer three things. First, we need to answer how many items are there in the struct that I'm unpacking. So square bracket, part 1, comma part 2, comma part 3. That means 3. So we'll answer 3 for that. The second thing we need to answer is the type of each of those, because behind the scenes we need to set up the types for those. We actually create some magic in the structural binding. That's why it always says auto there, because the struct that is created behind the scene by the C++ compiler, you don't know the type of that, but it still needs the type of each of the elements. So that's why we need the second thing, namely the types. And the third thing is the actual unpacking of the variable. So let's get started. The way that it works is that I will implement, first of all, I'll do a template specialization on this tuple size. And if I just press F2 here, you can see template, type name, TP, and I'm in utility, so that's something that comes with C++. Template, type name, TP, struct, tuple size. There is no implementation of that. That's what I'm specializing here. So structs, tuple size, MyStruct, and I must return the struct that I'm specializing must have a value that is a static int, and that's the number of items in there. That's number 1. Number 2 is the type of each of those, and for that I have this std tuple element now, and again it's the same thing. It's a specialization where I have both the type or the index of the element I'm talking about, so the 0 for the zeros for the first part of the tuple, 1 for the second, and so on, and the type of the struct that I'm supporting unpacking. And it looks like this. So MyStruct, that's the type that I support unpacking. Number 2, that is, if I scroll up here, 0, 1, 2, so that's the length that I have here. Number 2 is specifying this using type equal to int. That's this type alias mechanism that I can now somehow I can get my act on this. If I have a MyStruct, I can simply go std : tuple size less than 2, MyStruct : type, and that's an alias for an integer. I could do this for 0 and 1, 2, but I can also do the partial template specialization here of saying std size t index, and then they are both of them Q strings. And with this in action, I just need the third and final part, namely to get the value out of the tuple. I've specified how many elements are there, what are their types, and now I need to get them out. And for that, I need to implement a global method called get. It must take my struct as an instance variable, or as a variable here, and it's a template specialization on the index. And just like up here where I specialized for number 2, I could have done that, but I can also do this trick here and take them all 3 in one go. So if const expression index equal to 0, so that's the 0th element I'm asking for, then I'll just go to that struct that I got up there and return the base. And for 1, I'll return the extension, and for 2, I will return the length, which is again not an instance variable in that struct, but something I calculate on the fly. So implementing these 3 sets of methods or structs, I now support my own class. And it's boilerplate code, more or less. You can just take out of here. As I said, you're likely not going to need it all that much, mostly because that if you just have a regular struct, then it by magic works for all of your public instance variables in there. And again, you are more likely to just have stud pair or stud tuple or Q pair or Q tuple. Thank you for watching this episode on Qt Widgets and more, and until next time, have a great time.